Welcome to CS3308 Information Retrieval. This is the Unit 5 lecture, Part 1. During this lecture, we're going to talk about retrieval. Now, what exactly does that mean? Well, we've talked about a lot of things up to this point in time. We've talked a little bit about information retrieval as a solution. We've talked a little bit about the inverted index. We've looked at the concepts of frequencies of terms, how frequently a term appears in a particular document, how frequently that term appears across the entire collection of documents, which we call a corpus. We also looked at how we take that term and how we weight it, and how I can use those weights to calculate this thing we call cosine similarity. And if you recall, the whole idea behind cosine similarity is I take the weighted values that I have and I kind of plot them, if you would, on a two-dimensional or three-dimensional or n-dimensional graph. And when I plot them in that way, the points form a vector, and that vector we measure against another vector, and the other vector we're measuring it against is the actual query term. So when we plot that vector, and we can measure the angle between the query term vector and a document vector. And we do that because that allows us to get a good measure of how relevant things are because of how similar the contents of the document are to the query terms that were issued. And we use cosine similarity because, one, by measuring the angle, we eliminate the problem associated with Euclidean distance that we talked about. And so we want to measure the angle, and we use the cosine of the angle because it's always in decreasing order. So the biggest cosine is always the most relevant. The smallest cosine of the angle is going to be the least relevant. So we learned a lot of stuff about this, but what we have not looked at is how do I actually use that to go get documents from the index? And that's really the process of retrieval, and that's what we're going to talk about throughout most of Unit 5. So kind of the focus of the day is all about retrieval, and once I've got a process of determine what things are relevant, how do I actually retrieve them, and which ones do I retrieve, and how do I do the ordering? And so that's where we get into this, scoring and ranking. We've got a score. How do I rank it? Because what I really want to do is I want to get the most relevant documents first, the less relevant documents later. And so we run into an issue of how do we actually do that? So I have a gigantic index with lots and lots of documents in there, and I could go in and calculate the cosine similarity scores on absolutely every single one of them, and then sort it and return the results. Well, the problem with that is that when I get very large indexes, that can take a lot of computation to calculate all of those scores. So certainly sorting is one way of doing it. It is one approach that we can take. We can go out and say, I want to sort the cosine similarities of the documents, and I want to get the most similar ones first, the least similar ones last. And again, that's certainly possible to do when we get a very large index, however. And it's a perfectly reasonable thing to do, quite frankly, if I'm dealing with a relatively small index. It's just when it gets very large, I probably need a better approach, simply because it can take so long to do the computations of all of those cosine computations. So really, our focus in Unit 5 is going to be around how do I make this efficient, right? So we know how to get the best quality, and that's really to focus on our cosine similarity, look for the things that have the smallest angle or difference of angle between the query term and the document terms. But that isn't always practical, simply because the indexes can be so large. So what we really want to look at is how do I do this fast and still have good, relevant returns coming out of my search? So when we start looking at score computation, and when we say score computation, it means going out and calculating the cosine similarity of the document. This is going to be a significant amount of the CPU work of a query. So, if you think about everything that's going on in a query, the first thing is I got to go find the relevant terms in the inverted index. I got to go get the frequencies, and then I'm going to do the computation. And what we're basically saying is that that computation is going to be a substantial amount of that processing. So I have to be very efficient with it. Another point that we're gonna recognize is and you all probably know this empirically, and that is that when you go to Google and you type in your search terms and you click on the button that says search, it doesn't wait a long time before it comes back. In fact, it might seem that it's almost instantaneous that it starts returning the results, when in fact it's not. But generally, we're talking about something that's less than a second, and in fact, 250 milliseconds, which would be a quarter of a second. So we're saying I have to be able to do whatever computations I'm going to do, whatever I'm going to do to access the data from the index, and I need to do it in roughly a quarter of a second. So that doesn't give me a lot of time. Okay, so what that means is that I simply cannot exhaustively score every document and every query. I just can't do it. So I got to find ways to, make some good bets. I want to be able to make some good bets. I want to be able to kind of pick the documents and calculate the scores on the documents that have the most likelihood of actually being a good score or a high score. So part of what we're really focused on doing is in every search engine, we're going to want to focus on something we're going to call the top K. So we're going to say, somebody's not going to sit there and look through hundreds and hundreds of documents, or for that matter, thousands or tens of thousands or millions of them. They're going to look at the top few documents to maybe the top few dozen. So we have to have this concept of a top K. We have to keep in mind that the typical user isn't simply going to go and look through all of these things. They're going to look at just the few top entries and expect those few top entries to be the most relevant documents to match the query that they've issued. So that's where this concept of top K, and K basically is just a number. We're saying how many of them are we going to focus on? Maybe we're going to say we want to look at the top 10, maybe it's going to be the top 100, but basically this becomes the term of K, and this is going to be dependent somewhat on the efficiency of our search algorithm and the characteristics of our users and how they're using it. So, if I were to look at a K equals 100, that would probably cover just about any situation where a person is going to be doing searches. In fact, if you look at most indexes, you look at the way Google or AltaVista or some of the others work, you're going to find that you will scroll through a number of different things, and then it'll have a go to the next group of them. It doesn't list hundreds and hundreds of them on the same page. And essentially, what's happening is when I click on the next button, essentially what it's doing, it's revising K, and it's going to go and it's going to say, well, I'm going to take these ones off from the list, I'm going to go get the next 100, right? So essentially it's going to go through this process again, but it's going to do it in such a way that it's not going to go back and relook at this first 100 entries. So that's essentially how Google works. So I wanted to just kind of do a recap of the idea as a query as a vector. We've talked about creating vectors from a document, and the basic idea is that we're going to have the TF and IDF parameters, or the term frequency and the inverse document frequency, which is kind of looking at how frequently does a particular term or word appear in a document, as well as opposed to how often that word appears across all of the documents. So we're going to use that to calculate a weight, right? And I'm going to do the same thing for the query terms as I do for the documents. So essentially the documents get a vector that gets calculated for it, and the query itself becomes a document for which I calculate a vector for. And if you recall, one of the things that we said, and I'm terrible at drawing a straight line here, but when I take my query terms, and let's assume I have two of them, right, it kind of comes out as being a 45-degree angle, because each of the query terms has the exact same weight. So let's just say I had two query terms, home and mortgage. Right? Because each one of them has equal weight, because there are only two words in the entire document, and it's the two terms. It tends to be this 45-degree angle, and then what happens is that as I plot the vectors of the documents, they might be different trajectories out there. So for example, this might be my query, this might be one of my dockets, this might be one of the other documents, and then what I'm doing is measuring the angle of difference from the document and the query term. So hopefully you can remember how all of that works, some key ideas, and essentially that is what we're doing from the perspective of scoring. Now, again, this is saying I'm calculating this cosine similarity. I'm measuring the angle, and I'm looking for angles that tend to be small, and I'm using the cosine so that it's basically the inverse of it. So the larger the angle, the better, right? And that's how I'm ranking the documents. Now, again, the problem is that I can't do that calculation for every single document out there. So I gotta get selective in how I do that. And there's really kind of two approaches that we're gonna have of doing that. Now, two ways of computing this kind of boil down to the TAT or the DAT. TAT basically refers to term at a time. So basically the idea is that for every term that we're going to be evaluating, and maybe the terms are home and mortgage. So essentially what we're going to do is we're going to go and scroll through all of our documents and calculate the term and the weighting for home, and then I'm going to go back and do the same thing for mortgage. So this is kind of the idea of term at a time. And essentially I'm going to look at this one, and I'm going to come up with a group of things that match that. Then from that group, I'm going to apply this term perhaps, and all the things that match that. And that's kind of the term at the time. Document at time basically says for each document, I'm going to calculate both terms. So instead of getting a subset that I have, selecting from a term, and then from that group selected by that term, I then select a subset, and so on and so forth. Document at a time basically says I'm going to select by calculating each of the terms for the document at one time. And each of these has implications for how I actually retrieve them, and how I might determine how to limit the number of documents I'm going to actually have to calculate the similarity index for when I go do my cosine ranking. So again, the whole purpose behind this is to find the k number of documents. We talked about k. Maybe k is going to be equal to 10. Maybe k is going to be equal to 100. But the idea is that I want to get the 10 most, or the k most relevant documents that are out there. All right, and the objective would be is that I want to limit how many documents I have to actually calculate that for to find that 10 or 100 relevant documents. And so there's two approaches that we can do to do that. One of them we call safe, and the other one is non-safe. Now, the basic idea behind safe ranking is that we are going to have a guarantee that when I actually return k number of documents, so let's say k is equal to 100, safe basically means I'm going to ensure, I'm going to guarantee that those 100 documents being returned are the top 100 documents. No bones about it. I'm going to double check and make sure. Non-safe basically says it's okay if it's not 100% accurate. It's okay if maybe I didn't get the exact 100 top documents. Maybe if I got the top 90 documents out of the 100 that are retrieved, that's good enough. And that's the basic idea behind non-safe, is there a point at which it's good enough? Now, the reason this is important is that in some fashion, in safe, I'm going to have to go through pretty much all of the documents that match the query terms. I'm going to have to go through all of them. And I'm going to do it in such a way that I'm going to try to prune stuff. I'm going to do it in such a way that I'm going to use some of the advanced algorithm concepts that we learned in analysis of algorithms to make it more efficient asymptotically. But I still have to go through them all in some fashion. Non-safe says I'm going to take some shortcuts and I might miss some stuff. So we're going to, in the next two lectures, we're going to look at specifically at safe techniques, and we're going to look at non-safe techniques for actually going out and determining which documents we're going to retrieve. Now, if I didn't mention this, and probably should have emphasized this a little bit more, this whole process is about finding that set of documents, that set of documents that we're going to return back to the user saying, these are the documents that match the query that you gave. Now, if it's a web search engine, what we're going to return is the top web pages. And if we're looking through the Reuters corpus, which is the set of documents, or it's actually a subset of Reuters that we've been using for our assignments, it means that we're going to return some subset of the Reuters documents that matches our query terms. And so, again, in the next 2 lectures, we will be looking at safe ranking and non-safe ranking.